Hi everyone, I hope you're doing well. This is the first video of week 15. And as I mentioned last week, this week I'm going to go over the example and the practice problems for PE exam. So let me begin with the kind of a brief introduction of PE exam. As you know, the PE, the professional engineers exam, is kind of the highest level of, not the highest level, but I can say the general licensures for engineers, especially the civil engineers, that they can work as the professional engineers in the field. And we have every state may have a different kind of requirement, but for California, in addition to the 8 hour long, the paper version, um, the PE exam portion, that's the main portion, the morning and the afternoon. But California requires two additional subsections. Both are based on the computer-based testing now, so CBT, and each module will take 2.5 hours, and one for surveying, and the other one is the seismic. So everyone who'd like to get a PE license in California, they have to pass not only just the main portion of the PE exam, but also they have to pass the surveying and the seismic. That's one of the reasons that I initially create this course. And then I'd like to introduce these practice problems for my students so that they can be prepared for the PE exam in the future. Okay, so let me share the screen. So on the Blackboard, first of all, I uploaded the link. This is for the exam information, especially for the seismic portion. So when you click this one, you can see that this is the civil engineering examination seismic principle test plan. So they define the seismic principles. Is defined as a fundamental principles, tasks, and knowledges underlying those activities involved in the California practice of seismic design, seismic analysis, or seismic evaluation of new and existing civil engineering projects, such as buildings, non-building structures, non-structural components and equipment, and lifelines. And this exam has 6 primary content areas, and which is listed here. So seismic data and the seismic design criteria, which is 10%, characteristics of engineered structures, the system, 15%, seismic forces for building structures, 28%, seismic forces for non-building structures, components and equipment, which is 12%, seismic analysis procedures, 25%, detailing and construction quality control, which is 10%. And you can see more detailed items under each criteria. So for example, seismic data and seismic design criteria, which is 10% out of 100 for the seismic portion. It is related to the laws and the design codes and standards, identify design performance requirement, determine site-related coefficients, determine the effects of site characteristics on the structure, seismic design category. So we already touched some of these topics when we talk about the design code, right? For example, seismic design categories and risk categories and important factors. We already talked about those. Like this seismic characteristics of engineered the system and different structural systems and their design parameters. You can find it, for example, R factor. We have a very long tables in the ASC 7 code. Um, um, Drift and P delta effects, we didn't touch these. The damping on the seismic performance, redundancy. Some of them are covered, some of them are not in this class. So you can see those details. This one we covered most of it. So seismic forces for the building structures, which is 28%. Determine the structural characteristics required to calculate seismic design forces. We already talked about the equivalent lateral force design method to figure out the base shear first and then divide it into the equivalent lateral forces on each floor. Determine seismic design forces for structures. Perform vertical distribution of seismic forces for structures. Determine seismic diaphragm forces. Determine seismic force for structural elements. Okay, design space shear, the vertical force distribution, right? The selection of the seismic factors and coefficients for the required design, methods to determine the structure's fundamental period, static force procedures and formulas. So these are all the topics they already went through. Non-building structures, components, and equipment, we didn't touch these things. Seismic analysis procedures, depending on the analysis type and depending on the methodology, we have a different topics here. And then detailing and construction quality control, we didn't touch this one either. So bottom line, it is not 100% covered throughout this course, but we went through the not most, but the very important portion of this seismic principle testing. So based on those knowledges and the practice that we went through, we should be able to cover, I would say, more than half at least from these practice problem sets. Okay, so here is the first problem sets that I posted on the Blackboard. So I'm gonna go over this one by one today. Okay. All right, so let's begin with the first problem. For what kind of structures does earthquake design apply? By the way, the seismic portion of this PE exam is all multiple choice problems like this, okay? So A, bridges, B, buildings, C, both A and B, D, all structures. What do you think? In the previous, the plan, I said that, I showed you that this is for, not only for this building, non-building structures like, the bridges and other water tank type of buildings as well, and non-structural components and equipment and lifelines, right? So we have to think about all structural systems. We have to apply this seismic design, and the seismic design is going to be considered for all structures. So the answer is going to be D. Okay. The answer is going to be D. Okay, so I'm going to use the annotation then. All right, so the answer is going to be D. Second problem, the point on the Earth's surface directly above the actual location of an earthquake is known as hypocenter, epicenter, focus, faulting point. So we already talked about the difference between hypocenter and the epicenter. Epicenter is the Earth's surface, while this focus or the hypocenter is going to be the exact location of the earthquake itself. So the answer is going to be B. Focal depth is used to locate an earthquake's what? Epicenter, hypocenter, fracture zone, and fault plane. What is the answer? It's going to be hypocenter. So focal depth is the distance from the epicenter to the hypocenter, right? So we can locate the hypocenter, which is the focus, the exact location of the earthquake measured from the Earth's surface. So the answer is going to be B. Small earthquakes that may occur slightly prior to a large earthquake are referred to as A, aftershock, B, foreshocks, C, microearthquakes, D, tumblers. The answer is going to be foreshocks. So the answer is going to be B. Continuous or intermittent fault movement without noticeable earthquake is known as. We didn't talk about this, but the answer is A. So the crib, the definition of crib is this. Subsidence is kind of opposite meaning of the uplift. So we can think about the elevation is going down, that is subsidence, or we can also call it as a settlement as well. And lateral spreading is in the movement in the lateral direction. So the answer is A. San Andreas Fault in California is which type of the fault? It's just it's just kind of a fact. It's right lateral. So when we think about these two plates, here we have a Pacific plate. And then this is North American plate. And these two plates are moving this way. Okay, so the answer is going to be D, right lateral fault. Okay, next problem. A seismic sea wave, which is called tsunami, may be formed when fault slippage occurs on the seafloor of 1. Normal fault, 2. Reverse fault, 3. Strike slip fault. The difference between normal, reverse, so these two, what is the answer? What do you think? So these two are kind of the vertical movement, while this strike slip is kind of a horizontal movement, right? Horizontal movement doesn't create a tsunami because the tsunami is occurred due to the sudden kind of movement of the land in the ocean in a vertical direction. So the answer should be C, 1 and 2. Okay. All right, so this is how we're going to solve the problem. So we're going to move on to the next page. Which seismic wave is the most responsible for the strong ground motion portion of an earthquake? A. Compression waves. B. Surface waves. C. P waves. D. Shear waves. Shear waves is S waves, right? What do you think? What is the answer? We talk about this. We talk about the difference between P wave and S wave. So the shear waves will provide the most responsible for the strong ground motion. This is S waves. Okay. And compression waves are actually the same as the P waves. So this A or C cannot be the answer, right? So if you cannot, if you don't know whether this is going to be the surface waves or the shear waves, you just eliminate these two and it's going to be 50-50 chance, right? Anyway, the answer is going to be shear waves. Seismic forces in a structure are initially caused by what? What do you think? A, inertial forces at each level. B, ground acceleration. C, liquefaction. D, shear waves. So seismic forces in a structure initially caused by ground acceleration, and that will provide the inertial force later on. In liquefaction, that's a very special situation that, due to the ground shaking, the water comes up to the surface level so that the bearing stress or the capacity of the soil or the foundation will be reduced. That's we call the liquefaction. And shear waves, that's just one kind of the seismic wave, which is not the answer. So the answer is going to be B for 1.9. 1.10, the scale most commonly used to describe the intensity of an earthquake is a logarithmic scale, Richter scale, modified Mercalli scale, both A and B. What is the answer? The answer is going to be C. We use a modified Mercalli scale, MMI. And we will talk about the difference between magnitude and intensity of earthquake. And the question is asking about the intensity, right? So these two cannot be the answer. Both A and B, of course, is not. So the answer is going to be C. And what is the difference between magnitude and intensity? Intensity is very subjective measure, while this magnitude is a absolute measure. We have an equation, either moment magnitude or Richter magnitude. We have a specific equation. So when you put the energy quantity into the equation, we'll get the numerical number. While this MMI intensity measure, you probably remember 1 through 12. So depending on the description, so depending on the feeling or depending on the movement or observation of the damage or something like that, we classified it into different level. So that's the difference between magnitude and intensity. So the answer is going to be C. Okay, next problem. Intensity of an earthquake is based on the one, damage to structures, of course. Two, peak ground acceleration at the epicenter, maybe not. Three, effects on people. So 1 and 3 are subjective measure, while this 2 can be a very, the absolute measure. So the answer is going to be C for 1 and C, on 1 and 3. 1.12. In general, structural damage increases during an earthquake when which of the following decreases? So damage is going to be increased when the following is going to be decreased. The peak ground acceleration is the maximum value of acceleration of time history of the ground motion. So when peak ground acceleration decreases, that means our magnitude of the earthquake is going to be smaller, getting smaller, which doesn't make any sense. Richter magnitude, kind of similar. When we have a smaller magnitude, we expect to have a smaller the damage, right? So damage is going to be decreased, not increased. So it's not going to be the answer either. Building period and distance to the epicenter. Building period is kind of question mark, I would say, because remember that the response spectrum, typical shape looks something like this, but it is not, proportional or like, opposite direction. Sometimes when building period is longer, in general, very long period, we expect to have a smaller or the reduced the seismic demand. So decrease of the building period may increase, but it is not 100% true, because sometimes from here to here, right, we have a decrease in period, we have an increase in demand, but from here to here, even further decrease, we still have a decrease in demand as well. So this is not 100% true. It could be, could not be, right? But distance to the epicenter, this is absolutely true, because when you are far away from the epicenter, that means you're far away from the source of the earthquake, right? That will decrease the damage. In other words, when you're close to the epicenter, which means the decrease of the distance, you definitely will have a larger amount of the damage expected. So the answer is going to be D. Okay, an earthquake that causes minimal damage to structures, moves some heavy furniture, and is felt by everyone in the area would be assigned an intensity of what? So you have to have a table for MMI scale. I think I posted on the Blackboard, so let me go back to the course materials, MMI table. I don't think so. So let me just quickly Google it. So it only has a couple of them. Let's just go to the Wikipedia. Here we have 1 through 12 intensity level, right? So what was the question? Oops. Oops. Oh no. Come on. Okay, so it says that earthquake causes minimal damage to structures, moves some heavy furniture, and felt by everyone in the area. So some heavy furniture moved, felt by all, not nearly everyone, it's by all. So the answer should be 6, right? C. Okay, so sometimes we can see this kind of a problem. So you can just look up the table and then go through the descriptions to find out the answer. All right, 1.14. By the way, PE exam, you're allowed to bring any material. Okay, there are some descriptions like, the material should be bounded in the ring binder or something like that. But basically, you can bring any number of books and any, resources, even the PE exam prep book or all the textbooks and design manuals. So you can easily look up those informations. So the key thing to prepare the PE exam is that you have to understand where you can find those information. Okay, that's the most important thing. Of course, you have to be familiar with the material so that you can find out, where you can find those informations, or where you can find the similar example problems, or where you can find the equations and the formula to get the answers. Okay, a Richter magnitude earthquake of 5.0 magnitude represent how much of an increase in the measured amplitude over a magnitude 3.0 earthquake? So you have to have an understanding about the Richter magnitude scale. And this is the magnitude again, so we're going to use the equation. So the equation looks something like this. So log of E and the base is 10 is equal to 11.8 plus 1.5 m. So this E is the energy associated with this earthquake, and you just need to solve it for m. So this is going to be the magnitude. So the bottom line is, so the question is, here we have a 5.0 magnitude and 3.0 magnitude. What is the difference between these two earthquake in terms of the amplitude, right? So because we have this is a log function and the base is 10, and we have a 2 difference between 3 and 5, right? So in terms of the energy and in terms of the amplitude, it should be 100 times, so that when you plug it in here, it is going to be 2, right? So that is going to be the same as the difference in terms of the magnitude. Okay. To the next problem. So this is another type of the problem using this equation, the same equation that I just wrote here. So Richter magnitude scale, magnitude 6.8 earthquake would radiate how much more energy than magnitude 5.8 magnitude earthquake? So 5.8 to 6.8, we have a 1 magnitude difference. So here you can see my kind of a calculations here. So I plug it in 5.8, right, to solve it for this energy, and then calculate the case with, let me see, it's the 6.8 case, and take the ratio between those two, and it's about 32 times. So that means not just from 5.8 to 6.8. For example, magnitude 3 earthquake to magnitude 4 earthquake, or 4 to 5, or 5 to 6, 6 to 7. Any times when you see the difference in magnitude from 4 to 5 or 5 to 6, the difference is going to be 1. In terms of the energy, it is going to be 32 times, which is really, really big, difference, right? So the answer is going to be B. What if we have a change from 3 to 5? So the difference is going to be 2. Then it's going to be almost 900 times, right? Okay, so the answer is going to be B. Which of the following earthquake magnitudes and duration of strong motion would likely result in the highest level of damage to the structure? In other words, the highest MMI. So magnitude 2.5 with 55 seconds, magnitude 5.0 with 40 seconds, magnitude 7.0 with 30 seconds, magnitude 7.5 with 5 seconds. So we have to think about not only just the magnitude of the earthquake, but also we have to think about the duration. So I would say the 2.5, 5.0, these are too small, right? So I'm gonna erase these two answers. So let's just focus on these two choices at the bottom, the C and D. So 7.0 and 7.5, in terms of the energy, of course, we have a kind of a difference. But 7.0 is high enough to have a lot of damages to the structures. And in terms of the duration, 30 seconds to 5 seconds, this is really, really big difference. Okay, so I would go with the C as a final answer. The dynamic characteristics of a structure are a function of the structures. So here we have all 1, 2, 3, 4, 5, 6 different choices. Proximity to a fault, okay, weight, moment of inertia, stiffness, all of the above, both B and D. What do you think? Proximity to a fault, dynamic characteristics of structures are a function of what? Proximity to a fault? Well, it is not, because you remember the dynamics characteristics of the structure, which means when we solve the differential equation, we talk about the equation of motion, right? The equation of motion is function of what? So equation of motion we studied in this class, P of T, are function of the structures of, first of all, the mass, which is related to the weight, of course, and then damping, okay, is not directly related to the moment of inertia or anything else, and the stiffness directly related to this answer, right? So the answer is going to be not only just weight, but also the stiffness. So the answer should be B and D. So the answer is F. Damping ratio is defined as a ratio of what? So remember the damping ratio psi value. It is related to the C sub CR. So the answer should be C, the actual damping coefficient, which is C, to the critical damping coefficient C sub CR. So the answer is going to be C. Higher damping ratio has the following effect on the response of the structure to seismic loads. A, very slight increase in the period of the vibration. B, large decrease in the natural frequency. C, decrease in the base shear. D, both A and C. What do you think? So let's think about the effect on the damping. So the higher damping ratio means with a given critical damping, we can say it's gonna be the larger C value, right? So let's think about omega n, K over M, and omega D, that's a damped frequency. We can calculate it as omega n times 1 minus psi square. So here we can find out Tn. Here we can find Td. So if you have a higher damping ratio, that means we will have a higher amount of the damping, so that if we have a higher amount of damping, then omega n is going to be larger than omega d, because omega is Tn, no, Tn is going to be 2 pi over omega n, or omega n is going to be 2 pi divided by Tn. It's going to be inverse relationship. So if omega n is larger than omega d, then Td is going to be the damped period is going to be longer than the natural period. So higher damping ratio means not large decrease, so it's not going to be the answer. Very slight increase in the period of the vibration. When you have a higher value here, then it's going to be smaller, so we will have a longer period. So this is going to be right one. Decrease in base shear. So think about the base shear equation. V is equal to CS times W, and the CS is a function of SDS and R and I. And SDS value. So SDS is a response. This is coming from the response spectrum. So response spectrum, we have a spectral acceleration versus period. And when you have a higher damping, then we will expect to have a smaller value of spectral acceleration, right? So with a given period, we have a smaller value of the spectral acceleration, and this is inside of the CS. So I would say the decrease in base shear is another characteristics. So A and C, both A and C, so the answer is going to be D. All right, what type of structural system is likely to have the highest damping ratio? It is kind of a fact. The plywood, which is a wood material, concrete, steel, and concrete. So concrete is about 5% damping. Steel, a little less, 2% damping. And wood has about 15%. The answer is going to be A. Okay. All right. Let me stop here, and then I'm going to continue to solve these problems in the second video clip. All right. See you later.